Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life. And if it's one of your first times listening to our podcast, when we say that Melissa is a chemist, she very much, really, truly, actually is a chemist.
Wild.
She's got her PhD and also a master's. So
it's true.
That's sort of academic speak for she knows what she's talking about.
For so long, we were like, she has a master's and also working on a PhD.
Yeah.
And now we're here.
Yeah. And now we're here. And I don't have any of that stuff. And I'm definitely not a chemist. And I'm just a learner like you guys.
But he does have other skills.
Yeah. I bring some stuff to the table. But
definitely.
For y'all's purpose, I'm like you.
Yeah. And I do think you've learned a lot of chemistry, as we learned on our 100th episode when we gave you a test.
Oh, yes.
You do know a lot of chemistry now. You've sort of been studying it in a casual way for 3 years.
Yeah.
So
yes,
that's pretty impressive.
Yeah, it's more than I would have done if we weren't doing the podcast.
That's absolutely true.
I just don't think I would have studied as much chemistry, you know?
Something else that I feel like we've talked about some, but we haven't talked about lately. But last episode, I found out something I didn't know that I felt like I should know. So this is a good chance to bring this back up. Is a lot of times we talk about the fact that I'm a chemist, I'm an expert. And I think it's easy to assume that means so I must know everything, or I have all this knowledge of chemistry just at the tip of my fingers. And to some extent, that's true. I know a lot about chemistry, and I do have a lot of knowledge of chemistry right at the tip of my fingers, but I don't know everything. And what a lot of our episodes are is actually me taking something that I do know about the field of chemistry or about a chemical concept and then learning how it applies in a new situation. And so there will be times where I just don't know, or I might not get something exactly right. I get it to the best of my ability. And whenever that happens, we try to be really upfront, make the correction quickly, but also it's just a good thing of knowing that really experts more know how to get the information that they need, and they know a lot about what they don't know.
Yeah, right.
But they're not just people who know everything right off the top of their head. That's that's never what we've tried to do here.
Yeah, yeah.
So I think that's always a good thing to revisit and remember. And if I ever do make a mistake, or if anything ever comes up that we get feedback on, we always try to address it as quickly as possible.
Yeah.
And that is a mark of good science. If you get new information that's founded in evidence and you know that we need to revamp our thought process or our understanding of what's going on, that's good science. You want scientists to be always updating their information, just like your phone system or your computer system.
Yeah.
All right. Well, now that I've redeemed myself for not knowing a 20 carbon chain, to be fair, I asked a friend of mine who also teaches OChem, and they didn't know off the top of their head either.
Yeah. So it seems like it's the kind of thing that probably is not being asked of every chemist.
No, they said,
day.
Who needs to know that?
Yeah.
But Kaibe did write in about it, and I think maybe biochemists need to know about it more. So we'll probably share about that on the next Q&A.
Nice. That's cool.
Okay, so let's hop into this week's episode, which is kind of a part 2. It's more of a standalone, but a part 2 of last week's episode. So it's inspired by Julian E., who asked, how does the catalytic converter in a car's exhaust system work? So last week we talked, or 2 weeks ago, I guess, we talked all about gasoline and how gasoline makes your car go. And then now we're going to talk about what happens after the gasoline is burned to the gas that's emitted after that.
Okay.
So a very, very simple way to answer the question of what a catalytic converter does, not how it works, but what does it do, is I think of it like an air filter to reduce pollution.
Okay.
Did you know that already?
No.
I didn't know either. I didn't really know what the catalytic converter was for. I had suspected that it was some kind of chemistry reaction based on the catalyst.
Yeah.
But I didn't know what its purpose was at all.
Yeah, and I've heard it just talked about as like only in the context of an everyday person needing to know it, where it's like, oh, so-and-so's car got all messed up. They had to pay a lot of money to get this done. And one of the things that needed to be fixed was a catalytic converter or something like that.
Yes.
I've absorbed the knowledge that it's important for the car and that that's all I've got.
So yeah, it's important for the car, and a lot of times it actually gets stolen rather than even getting messed up because there's some precious metals inside of that
that people
are trying to reuse for other things. But really, yeah, all it does, and in some ways it's not really essential to the functioning of the car itself, as far as I understand it, but it is required to be in the car. So if it gets stolen, you do have to replace it.
Got it.
But all it does is take the gases that would be emitted after the combustion reaction of your gasoline and sort of filter them to make sure that there's not a lot of pollution getting out, to significantly minimize that pollution.
Okay, that's cool.
And yes, it is cool because some gases are really bad for us to breathe in.
Right.
So pollution can contribute to asthma, lung cancer, and then other respiratory diseases. We don't know a ton about the long-term effects of pollution, so I'm sure there's other stuff we don't even know about yet. And they also can contribute to climate change.
Right.
And as much as we love talking about climate change, and we have talked about it before, I would love to have Dr. Collini back on to talk about how greenhouse gases impact climate change.
Right.
But we're not going to talk about it today, just that there are gases that are not good to let out into the environment.
Okay.
And the government has recognized that. And I think that's actually part of why in Texas we have an emissions inspection.
Yes. Yeah.
Part of our annual inspection.
Some states do not have that and don't even have annual inspections at all.
Yes. And I was trying to figure this out and I couldn't quite. But I know the FDA put out a Clean Air Act. And I think in that Clean Air Act, they require catalytic converters to be in cars. But I don't think all states have the annual inspection. So maybe when they're produced, they check it.
Right. Yeah. Maybe it's like when it's for it to be sold or something like that.
Yes.
But yeah, I know in Indiana, where my wife is from, they don't have annual inspections at all. Mm-hmm. It's kind of crazy. It's like, you'll see some cars on the road that you're like, that would not pass down here.
That should not be driving down the road. But so I'm thankful actually that we have that inspection because it helps to make sure, that there's the minimal, I guess that the air filter, quote unquote, is still functioning.
Yeah.
And we're minimally contributing to climate change. It'd be nice if it was like free though or something.
Yeah, that's true.
It's always such a headache because it's like you got to get your insurance and then you got to go get the inspection done and it costs however much money and I'm always late. I always forget about it. It's like very chaotic.
Yeah, it definitely is.
Or if you could just do a quick drive through and they'd be like, check, you're done. And that's it. And you don't have to go through all the other steps and you just get the sticker right then.
Yeah, that'd be nice.
So anyway, but I'm thankful that they want our air to be clean. I think that's important. So shout out to the government for that.
Yeah.
But one thing that I think is important to realize is that there really shouldn't be those bad gases coming out of the car in the first place if you think about it theoretically.
Okay.
Because we have hydrocarbons, which is just carbon and hydrogen. And in theory, it's reacting with pure oxygen. And that should just be giving us CO2 and H2O.
Okay.
And both of those are okay to be in the environment. We breathe out CO2, plants breathe in CO2.
Right.
That should be fine. And water, water vapor is just water. So that should be fine. So what's going on with that?
Yeah, what is going on with that?
What is going on with that?
now that you've said that, and now that I am like, oh, that doesn't make any sense. So how does bad stuff get in there?
Well, this is a classic organic chemist problem because on paper and what we learn in school, we have talked about this a little bit before, but we think of it as A plus B is going to yield to C. That's like the A plus B and there's an arrow and it gives us C. And the way it's written sort of is all C, nothing but C. It's just C. Uh-huh. But in real life, it's like A plus B reacts to give us C. And then some C might react with some A to give us something else. And some C might react with B too, if there's any left over. And then two A's could react with one B and all kinds of other little side products happen. Uh-huh. And so really when I was in the organic chemistry lab, I felt like I got A plus B with mostly C and then also D, E, F, G. And you had to do all these purification techniques to isolate the big product that you really wanted.
Okay.
And that's also why it's not really super safe. I don't know how many of our listeners are doing drugs, but it's not super safe to buy meth that's made on the street or other drugs, but I've heard about it most with meth, is because you're going to get side products, and only chemists who are really good at their jobs can really isolate so you only get the one thing that you want.
Right.
And so it could be laced with a lot of other dangerous things.
Yeah, okay, that makes sense.
And that's also why it's important for pharmaceuticals to be regulated, because in pharmaceuticals, they do these multi-step reactions as well. And at the end of the line, again, you really want to make sure that your product is purified.
Right.
So we hope that we have a combustion reaction that gives us all water and carbon dioxide, but in reality, there's probably some nitrogen gas in there, or maybe there's even nitrogen from impurities in the gasoline. I don't think so. I think it's mostly from nitrogen gas in the air. But you get nitrogen oxides and carbon monoxide, and then hydrocarbons that just didn't react. And all those can sometimes come out of our cylinders into our exhaust pipes as dangerous byproducts of the reaction.
Okay.
So essentially, either it doesn't fully get reacted, or it produces side products that aren't desirable from the reaction conditions.
Okay.
So that's why those are even there in the first place. And I think that's a really good chemistry lesson just in itself. This is chock full. There's like 3 different chemistry lessons in here. So the goal of the catalytic converter is to get rid of those bad side products. It's basically being an organic chemist, right? It's like purifying out the things it doesn't want.
Okay.
So that's its job. Really, I guess any kind of chemist that does synthesis. There's inorganic chemists who do synthesis too.
Okay.
And it is metal. So maybe it's an inorganic chemist. But so when combustion engines have their emissions come out, those emissions pass through what's called a 3-way catalyst.
Okay.
And the 3-way catalyst serves to do 3 main things. That's why it's called 3-way. Is one, there's nitrogen oxides, and that's nitrogen bonded to 1, 2, 3. I don't think there's many beyond that, but at least 3 oxygens.
Okay.
And that will be stripped of its oxygens and become nitrogen and oxygen gas.
Okay.
Nitrogen gas and oxygen gas, which are fine to be in the environment. We breathe in oxygen, and nitrogen is just like inert in the air anyway. And then there's carbon monoxide, that is carbon with 1 oxygen instead of carbon with 2 oxygens.
Mm-hmm.
Carbon with 2 oxygens, again, fine. Carbon with 1 oxygen, not great for us to breathe in or to be in the environment.
Right.
And then there's also those unreacted hydrocarbons. And so carbon monoxide gets the oxygen added to it to become CO2.
Mm-hmm.
And then the hydrocarbons also get oxygen added to them to also become CO2, and then the hydrogens to become water, H2O.
Got it. Can you say, so carbon monoxide is one of the things that is produced that we're trying to get rid of.
Mm-hmm.
Hydrocarbons that didn't fully react.
Mm-hmm.
And then what was the first one again?
Nitrogen oxides.
Nitrogen oxide. Okay, I want to get those 3 like kind of down before we got too much further along. Nitrogen oxide.
Good move.
Okay.
So nitrogen oxides really get broken down into N2 and O2.
Yeah.
Carbon monoxide becomes carbon dioxide.
Okay.
And hydrocarbons basically finish the reaction they're supposed to start in the first place without the combustion.
Yeah.
And it becomes CO2 and H2O.
Okay, got it. Sweet.
Okay.
A lot of letters, a lot of things. I was like, I want to get these straight. That makes sense.
So nitrogen and 1, 2, 3 oxygens. Carbon and 1 oxygen becomes carbon and 2 oxygens. Hydrocarbons become carbon dioxide and water.
Got it.
Okay, so that's what happens as it passes through. The gases pass through this catalytic converter. So if you just wanted to stop right there, I guess you could. And that really tells you how it functions. It sort of acts as an air filter by using a catalyst of some kind to change those bad gases into neutral or good gases.
Mm-hmm.
So that sort of answers the question. And you did get a chemistry lesson out of it.
Yeah.
So if you're like, okay, I'm done, this is a good place to bail out. But if you're with us and you want to dig in deeper, I'm going to talk about what the catalyst does and then also what these reactions are.
Okay.
And I think this is a really fun episode because of all the little chemistry lessons in there.
Nice.
Okay, so any catalyst job really aids in a reaction and make it happen more quickly and easily.
Okay.
And we've talked about that before, maybe as it like lowering the amount of energy that it takes to make the reaction happen. But I like to think of it just as it being sort of a helper that's present, that's going to do whatever it needs to do.
Okay.
So sometimes in organic chemistry, we add a little bit of acid to help move things around. And in this case, the catalysts are metal, and metals are good because they end up giving electrons easily or taking electrons easily without their identity really being changed too much.
Got it. Okay.
And actually, I kind of think of these are specifically those transition metals, which are the metals in the middle of the periodic table that are good at doing that because they sort of have a lot of extra electrons around.
Okay.
So you can kind of think of the metal catalyst in this case as sort of a sea of electrons, just a bunch of electrons. And some metals are better about giving up electrons and some are better maybe about taking them in. But ultimately, they're there to either take on or give up electrons because it's not a super big deal to them. I kind of think of it as maybe the oxygens and nitrogens and carbons that we talk about a lot don't have very many electrons. They're in the very, we talk about sort of the valence shell, but so their valence shell is really close to their center.
Okay.
So if you gain or lose one, they don't have a ton. And so it's kind of like, oh no, I lost an electron. That's a big deal, you know?
Yeah.
But if you're on the if you've got several layers of electrons and you gain or lose one, the center of the atom may not even know.
I see. Okay.
Like maybe someone who's really poor loses $50. That's a big deal. Or even someone who, college students, it's a big deal. They're closer to the beginning of their
Right.
finances. $50 is huge, but to most adults with children, they're dropping $50 for things left and right.
Yeah, right. Yeah.
You know, it's a sort of a scale of like, oh, if you have less money, it affects you less. And if you have more money, if you have less money, it affects you more.
Yes.
Let me say that whole thing over again. Sort of like a scale. You know, if you don't have a lot of money and you take some of it away, that's a big deal.
Yes.
But if you have a lot of money and you take that same amount away, it might not be as big of a deal.
That makes total sense.
Yeah, so metals are like the rich in electrons. They don't really care. If they get a little or lose a little, it doesn't really affect their stability overall.
And that's cool because one of the things I was kind of wondering as we were building toward this was just how could something be a catalyst that we build into our cars and how could it do it continually?
Yes.
You know, how are we not needing chemists to come by our houses while we're sleeping and put more catalysts in all of our cars? How can it keep doing the same thing over and over?
Well, a lot of catalysts regenerate. I don't know if that's required of being a catalyst, that it has to regenerate, but like in organic chemistry, we will often add a small amount of acid, and what happens is one atom will take on that acid that's usually in the form of like a proton and hold on to it. And then the reaction will happen and then it gets released in the end. And and then another one will take it and hold on to it. And then it gets released so another one can take onto it. So it's sort of by the end of the reaction and the acid is taken in, but then it's produced back up.
I see.
And so I don't know for sure if metals are that same way. I think that they are, but I think the electrons do maybe get regenerated. I don't know for sure, but I think maybe there's not a huge net loss of electrons.
Right.
So I'm not an organic chemist, and I did not look that back up before we did this episode. I probably knew that once.
Well, it still sounds like what you're saying is a good situation for them anyway. If they can give up electrons and gain them back, and it doesn't really affect each individual atom very much,
right?
Then you imagine that happening a lot over and over. They're probably as good as you could hope for, to be doing this job.
But I don't think the metal gets degraded too much as a result, which might be because electrons do end up leaving and coming back.
Okay.
I think.
Yeah, that would seem to make sense. But even so, it's still, I don't know. It still kind of answers one of the thoughts I had, even if it's not completely certain. But I was just thinking like, there's not some just chemical sitting in there that could be depleted, you know?
Right, no.
There's not some, so it's like, it's a solid metal piece of something that can keep doing that.
And even if it is getting eaten away one electron at a time or whatever, that is still a long lifetime because there's so many electrons present.
Right.
Because 1 mole of something has however many 1.0 2 times 10 to the 23rd atoms present, right? Yeah, that's a lot of atoms, and all of those atoms have electrons, so there's just a lot of electrons there.
Y'all couldn't see it, obviously, but I just kind of did this like all the numbers were just hitting me, and like my eyes were rolling in the back of my head, and I couldn't compute it. That's what was happening in the silence.
I was just throwing really big numbers, and Jan was being mind blown actively.
Basically, anytime Melissa says the word moles, I already kind of just know I'm not going to really get what's happening afterward as much. Moles were one of those big stumbling blocks for me back when I took chemistry, and I just tried so hard that they're so hard for me to understand. But maybe that's a thing for another day.
Well, yeah, that's definitely a thing for another day. All you need to take away from this is it's a lot of electrons, and I think all catalysts have to be regenerated, although that might not be true. Inorganic chemists, don't come at me.
Okay.
This is a good example of how I'm not an expert in everything. And the episode was focused a different direction, so I didn't take the time to look this up. I was doing other things. So what can you do? You can't look up everything and anticipate every question.
Right.
And take note of that. If you're a teacher, your students can tell when you don't know, so don't try to BS your way through it. Just say, I don't know. I think this way, but I don't want to mess you up. So we can come back to it. Send that to me in an email. That's what I always say when I don't know.
Yeah.
So it's a lot of electrons. It's a sea of electrons in these metals that our gas emissions are coming to.
Okay.
And so they help facilitate the reaction by having all of these electrons just around. Okay. And they're ultimately, they just make it easier to do the reaction.
Okay.
So the type of reaction that they're facilitating is a specific kind, and it's one we have talked about before. Can you guess, based on what I've told you, that nitrogen oxides become N2 and O2, and carbon monoxide and hydrocarbons turn into CO2 and water? What kind of reaction this might be? What?
It's like, is it as obvious as I think it is?
I don't know. What do you think it is?
Is it oxidation?
Yes.
I was like,
I don't think that's obvious to everyone.
Yeah, it just seemed like, okay, everything's getting oxygens. Maybe it's oxidation.
Not everything is getting oxygens, but yes.
Yeah.
Lots of things are getting oxygen. Yay.
Nice. I was like, this is a trap.
No,
There's
it's
no
not.
way.
It's not. I wanted to take that as an opportunity for you to grow your confidence.
Okay, good. I'll take it. I'll take any of those opportunities I can get.
So it's both an oxidation and a reduction reaction is happening. Both of those are happening.
Right. And I remember that it was oil rig. Oxidation is loss.
Of what?
Of an electron.
Mm-hmm.
And reduction is gain.
Uh-huh.
Because electrons are negative.
Yep.
Got it. Okay.
And we talked about that basically oxidation reduction can be conceptualized in kind of two ways. And I think Gen Chem takes the oil rig way, where they focus on the movement of the electrons.
Right.
And we've done an episode where we talked about it that way too, especially about rust. Do you remember that episode?
Yes.
And so we talked about, oxidation is losing electrons. Losing electrons makes you more positive because it's negative. And reduction is gaining electrons. Gaining electrons makes you more negative, and that's why we call it reducing.
Right.
But then in OChem, we kind of conceptualize it in a separate way, which was always a little bit easier for me to grasp than why it was called oxidation.
Mm-hmm.
Not the reduction part, but oxidation and reduction in OChem is gaining bonds to oxygen is oxidation usually, and losing bonds to oxygen is reduction. And you can broaden that out even further and say, like, gaining bonds to anything that's more electronegative or has the tendency to have a lot of electrons around it is oxidation, and then losing bonds to that and replacing it maybe with something that has less electronegativity than less electrons around it, that's reduction.
Okay.
So we have had those two separate ideas of oxidation. Oil rig, reduction is gaining electrons, oxidation is losing electrons, and then OChem definition, oxidation is gaining oxygens, and reduction is basically losing oxygens.
Got it.
So, which is weird.
Yeah.
So
that is weird.
they don't feel like they go together. And what I'm so excited about in this episode is it does kind of show you how they go together.
Okay.
And if you are in Gen Chem or you remember Gen Chem, you could try to write out the little half reactions where it has the elements and the electrons. Like you write out electron as if it's one of the reactants. You know, if you remember that, this might be a good exercise for you, but you don't have to worry a ton about that.
Okay.
And I'll connect it for you. So if you think about it, most things are bonded together because they want this proper number of electrons, especially in the lower elements or the ones that are smaller, so that they're the poorer ones. They don't have as many electrons.
Uh-huh.
They really need that good number of electrons to be more stable.
Okay.
So if, for example, we have nitrogen and oxygen, nitrogen has 5 electrons, oxygen has 6. Neither of them have the really 8 is kind of what they're looking for. So neither of them really have 8. So they'll come together and share electrons. Maybe they'll need to scavenge one more. And that way, with the sharing, it seems like both of them have roughly 8.
Okay.
So if you're trying to break those apart, usually what would happen if you're trying to break a bond like nitrogen and oxygen is, one, it takes work to break apart a bond. And usually one of those atoms is better at pulling electrons towards itself than another. So if I have nitrogen and oxygen, oxygen is better at pulling electron towards itself.
Okay.
So if I broke them apart, oxygen would probably be have more electrons around it and would maybe be more negative. And then nitrogens would have less electrons around it and might be more positive. It needs electrons.
Okay.
So if I broke them apart just when they're by themselves, say in the middle of nothing, and I have one nitrogen and oxygen, they're bonded together, they are sharing enough electrons to have 8 between the two of them for each of them, and then I split them up, there's going to be a negative oxygen and a positive nitrogen, and they're going to be mad that they were in a good situation and got taken from them.
Got it. Okay.
So it's very hard to do. It takes a lot of energy. It takes a lot of work. They're not going to want to do it. But if you take that same thing and plunge it into a sea of electrons, that same nitrogen and oxygen bonded together, and you break them apart, they may still be charged, but this nitrogen can pick up the electrons it needs to get to neutral, and maybe oxygen can drop one off or bond with the metal or whatever it needs to do to be neutral.
Uh-huh.
And then now everybody has their 8 electrons again, because instead of just breaking apart when they were totally alone, they got to break up in a sea of electrons that could basically meet their needs, and they could pick up or drop one off as needed.
Got it.
And that is why gaining and losing oxygen bonds is also sort of an oxidation reduction reaction, right? It's the electrons needed to be moving around that's part of the reaction that's happening.
Okay.
But in OChem, because we mostly only see oxygen in these specific ways, we simplify it way, way down to just saying bonds to oxygen gained or bonds to oxygen lost.
Okay.
But in general chemistry and inorganic chemistry look at the whole periodic table. So they don't simplify it down just to looking at oxygen.
Okay.
But our main player of of electrons moving around in that way is oxidation reduction.
Right.
But you can see when I describe it that way that the electrons being present and are still moving around, even if we're just talking about bonds increasing to oxygen or bonds being taken away.
Right.
So really what happens when your nitrogen and oxygen are in this sea of electrons, they get broken apart. Then the nitrogen can be stabilized by the electrons in the metal, and the oxygen may be also, it might take as many electrons as it needs to be stable by itself. But if it wants to form O2, which is better, it can find another oxygen. They can drop off their extra electrons.
Right.
And then the nitrogen is stabilized until it can find another nitrogen, and then it becomes N2, which is stable gas. And if they need any extra electrons, they have them there, and then they can go off. But I think when they find each other, that takes care of it.
Right.
So I think that's why the net electron is no change.
Okay.
So essentially, we have our nitrogen losing its oxygen, so it's being reduced. It gains electrons from the metal catalyst and then can form N2 with another nitrogen. And we have oxygen that's set free when it breaks away from the nitrogen. it finds another oxygen, but if they both have a lot of electrons around them, they'll need to drop some off before they can go. So it's being oxidized. It bonds to an oxygen, so oxidized, and also losing electrons.
Right.
So that's where those two concepts come together.
Yeah.
You need the movement of electrons for bonds to be made and formed.
Okay.
So nitrogen, in that NO2, the nitrogen gets reduced and the oxygen gets oxidized.
Okay.
And that's how we end up with N2 and O2.
Got it.
And something similar happens with the carbon monoxide when it is able to take in another oxygen. Then we call that an oxidation reaction and it becomes CO2. Or if carbon and hydrogen, what happens to them is each of them also, carbon becomes carbon dioxide, it adds on 2 oxygens, and then the hydrogen, 2 hydrogens get 1 oxygen.
Right.
And so that metal that is present in our cars is able to give and take back electrons as it needs to and stabilize the atoms in the meantime until they can find each other and become this new thing very easily.
Right.
And that's how catalytic converters are able to take toxic emissions and turn them into, it filters it by doing a chemical reaction, oxidation and reduction, to turn it into safe air to let out.
Dang.
Isn't that amazing?
That's crazy. Yeah, it really is a lot more interesting than I expected it to be. And also, catalytic converter, I would have never guessed it was doing that much cool stuff.
I know.
It just seemed like one other car part.
Even if someone just told me it basically filters the air, I think I would have thought it just captured the bad stuff.
Right, right. Just like an air filter would, like, in your house.
Yeah.
You know, I'd thought like, oh, it's just getting the dust and stuff.
Yeah.
You know?
But no, it's neutralizing it, basically. It's taking it from something dangerous to something safe.
Yeah.
Kind of.
Yes. Yeah, and filtering, I mean, I guess you could say the word filtering, but that makes it sound a lot more passive.
Yeah.
And this is like, oh, no, this is...
It's converting.
Yeah, converting some stuff.
Yeah.
That's very crazy, dude.
Yeah. So I hope it wasn't too complicated. I try to sort of build up where it's like, okay, it's a filter. It filters by doing oxidation reduction reactions. And then literally here's the role of the metal. It's acting as a sea of electrons to stabilize things as they break apart and reform.
Yeah. Yeah, I don't think it's too complicated. I think I tracked with it. The hard part is how to explain it back. And also if I can think of any analogy that could help it, but I don't know if I can.
Well, the only analogy I thought of is like if you go through a breakup when you have friends around you. But then I don't know if that really gets at the like gained and lost because it's not like one person loses friends, or I don't know.
Yeah, yeah.
So that broke down for me, and then I gave up and decided I would let you do it.
I think I have sort of an idea brewing in my head. The only analogy that's really come to mind, branching off of your like money analogy you used earlier, just about catalysts having plenty of electrons.
Mm-hmm.
It would be similar to people having plenty of money and losing $1 or $2 here or there feels insignificant when you've got hundreds of thousands or something like that. So in this case, I kind of thought like catalysts could be like banks.
Yes. Okay.
And there's like, especially like think a big bank that, has multiple locations and all that stuff. But in general, at their disposal, they have so much money.
Yeah.
And people can, even organizations and stuff, can interact with this bank and get what they need. They can borrow money.
Yep.
They can just withdraw money that's really theirs, actually.
Mm-hmm.
They can come deposit money. There's all this happening on this large scale where a bunch of people are all putting in money, borrowing money, taking money out. And it's all changing hands quickly. But because this bank has so much, it can meet all the different needs of different people.
Yeah.
Some people are coming and they actually are trying to just put money in.
Yes.
They're trying to offload some money.
Yes.
Other people are coming and they need to borrow some to buy a car or a house or whatever, or to take out a loan for any number of reasons.
Right.
And the bank being this hub that has such an excess of it, that's available to use, can solve all the specific problems that people have.
I think that's great.
Which would be kind of like, so you've got, you have more electrons than you need, or than really would be good for you to be released out into the air.
Right.
Or you're paired with something, if you're NO2 or whatever.
Right.
And you need to have a wealth of electrons to change that up
So you can break apart from each other.
Mm-hmm. And have the ability to it's like starts to break down. Obviously, the bank thing breaks down, but it still works in the sense that like you could go way down the rabbit hole and be like, oh, two people need to break up. They need some money, or whatever.
Well, I like that bank. I'm thinking like maybe something like NO2 or just NO. There are different denominations of oxygen. So we'll just say NO. They need to break apart, but so that the N's no longer dependent on the oxygen for its electrons.
Yeah.
So maybe it's like if a kid goes to college and they take out a student loan.
Yes.
And then they go through college, and by the end, they have become a stable, safe thing to release out into the world into a college-educated person, and then they can go and be a productive member of society.
Yes.
And then they can, return back their money to the bank.
Yeah.
But I do think I should have done the math on this. I think nitrogen might net gain electrons even when it bonds with another nitrogen.
Okay.
But that's neither here nor there.
Yeah.
So they take this money, or maybe, they're given a scholarship from the bank,
Yeah.
and they take this money and they're transformed into a more stable, safe person.
Yeah.
And then the O2, if you have NO and it breaks apart, both of those oxygens are going to be negatively charged, like O2 minus. Both of them are negatively charged. They have a lot of extra money, and it's really not going to help them. They don't need that many electrons to be happy, so they start a scholarship fund or something. Maybe something like that, you know? And to the bank, it's like, we're fine. We can handle all this coming in and going out, and we're changing all this money, and we even can create interest from it all being here. It doesn't really matter, but we can take money in and send money out to who needs it and who doesn't. And it's not directly going from the nitrogen to the oxygen. It gets like through the bank's money first and then back out, maybe something like that.
Yeah. And you could even say like, I mean, if we really wanted to keep going, you can come up with all kinds of stuff. Like, okay, say it's NO2 and it's one of them is the apprentice under somebody else learning a trade.
Yeah.
What would be ideal for them to be out on their own is they could get a business loan, go start their own business, and then be separate from, it's like you could make up a lot of stuff. But
I do think that's a good analogy because there's a wealth of funding inside of a bank.
Yeah.
And it is changing hands a lot very quickly. And I do think that happens because it's not just NO that's being changed. Also, hydrocarbons and carbon monoxide are also being impacted.
Yes. But at the same time, it's all happening very fast.
Right.
But it's never quite significant enough where it's like, bank ran out of money.
Right.
It's all, there's so much there that it can come in and out on this consistent level and not change the nature of the bank's existence and stuff, which seems like to be the case with how much electrons the metals have in the catalyst. But so that's all I can think of analogy wise.
I think that's good.
And maybe just let me spit out some of the things that you said to make sure I understood them. But it's just that the NO2 needs to go in. It's bad for the environment.
Mm-hmm.
It needs to go into this catalyst. And this is a byproduct of the reaction in the engine of the hydrocarbons reacting with oxygen and burning or whatever, empowering the engine. But NO2 is...
It could also just be NO. Or NO3. Usually they write it as NO with a little X, like to indicate could be several.
Okay, got it. So lots of different ways of that none of them we want out in the air.
No.
And so if we can successfully pull them apart and have nitrogen be happy with just another nitrogen.
Yep.
And oxygen to be happy with just one other oxygen.
Yep.
And so when they go into the bank, they're waiting until things can happen that can let them leave that way.
Yep.
That's what they're hoping for.
Mm-hmm.
That's what we hope for too.
Yes.
With the hydrocarbons going in, they're ones that should have reacted but didn't. And so they're left over sort of from the original engine piston situation. And they need to be, before they leave the bank, they need to go from being a hydrocarbon to being H2O.
Yes.
And carbon dioxide.
Yes. So the carbon and hydrogen, basically, you can imagine those sort of separating out. And
Yeah.
then the hydrogen will meet up with another hydrogen and oxygen.
Yes.
And the carbon will meet up with 2 oxygens, and then they're set forth.
And the last one, or I guess earlier you said this in a different order. Sorry, I missed it.
Oh, that's okay.
But the last one is carbon monoxide.
Yes.
And so that one coming in to the bank, we want to equip it with another oxygen.
Yes.
So that'll be carbon dioxide.
Yeah.
Before we release it into the world.
Yeah.
And those are the 3 main things that this catalyst is trying to change, filter out before the leftover elements and atoms are put out into the air, basically.
And it has a pretty high efficiency, but it's not perfect.
Okay.
So there is obviously still some emission. There will always be. And I mean, unless we can get a literally 100% perfect chemistry reaction, which is hard for me to imagine.
Right.
And that's why, it's still important that you're careful with the environment. And if you've ever heard, you shouldn't keep your car running in a parked garage.
Yes.
Because you can get carbon monoxide poison. I've also wondered if part of the carbon monoxide poisoning might also just be like asphyxiation, where they're not getting enough oxygen, because there's also a lot of CO2 being released. I don't know, though.
Yeah, I wondered that too. Or like there's been times, there's horrible stories of carbon monoxide leak in someone's house because of like gas or whatever that they're natural gas that they use for heating or cooking or whatever.
Yes.
And then I wonder the same thing. Is it because the ratio of how much they're breathing got way off and they weren't getting oxygen?
I think it's a little bit of both. I think carbon monoxide can cause, if you breathe that in, I think it can cause physiological symptoms.
Yeah.
But then I think also if you're not getting enough oxygen, like if nitrogen's fine to breathe in, but you can't breathe in only nitrogen or you'll die.
Right.
So sometimes there's like a liquid nitrogen tank in our chemistry building, and it's in a small room. And so you have to keep that door open when you're filling up a liquid nitrogen tank, because nitrogen is more dense than oxygen. So if there's a lot of it, the liquid nitrogen it sinks to the ground.
Yeah.
And then it eventually just becomes nitrogen and disperses out in the air, and it's fine.
Right.
But when it's in that liquid nitrogen state, it's really dense. So it goes down. It almost looks like dry ice, when it does the steaming thing and it goes down on the ground.
Yeah.
But if you were to do that in a closed room and you're filling it up with liquid nitrogen, and liquid nitrogen, it sinks down to the bottom, but then it would slowly start filling up the room with nitrogen atoms, and you might not get enough oxygen.
Yeah.
So that's very dangerous. Yeah.
Wow.
So I've wondered if the carbon monoxide does obviously its damage if you park your car in a garage and leave it running with the garage door closed. But also if you aren't getting enough oxygen, I wonder if there's sort of like a double whammy of carbon monoxide poisoning, plus you're breathing in such a low percentage of oxygen, pure oxygen. You're just getting CO2 and nitrogen, and then also carbon monoxide, if that's also dangerous.
Yeah.
So I've wondered about that, but I don't know.
Yeah.
That's another episode for another day.
Yeah. Interesting.
And then I've also thought how impressive it is to me that catalytic converters are able to do this, because I think technically the way it works is first it runs through 2 different types of metal. So there's rhodium and platinum, and then there's platinum and palladium. Mm-hmm. And so I think the rhodium is it's better at the reduction reaction. So the nitrogen gets its oxygen stripped away first, and then maybe that oxygen then goes to the next plate of metal, which that plate of metal is the platinum and palladium, and that helps facilitate the oxidation reaction. And so I wondered, because to me, I'm like, there's so many moving pieces here. We're trying to make sure that every gas gets converted to a safest version in this order where it's not going to react backwards, and the nitrogen is also going to be converted back. And it's hot in there because cars are hot, and some of them, to make the reaction happen easier, they'll preheat it up. And then it's also, I think, under some amount of pressure, probably not a whole lot, but there is gas flowing into an enclosed space.
Right.
And so it just feels like so many moving pieces that much like airbags, I'm very impressed at the efficiency.
Yeah.
And I think it'd be hard pressed to find something else that's as efficient. And I would almost think there would have to be like 2 separate chambers, or I'm like, this could be something really hard to get right. And so I think that this is very impressive. I should have probably looked into who invented it and how hard it was, but it's already a long episode.
Yeah.
So, but I loved it. I thought it was so cool that I finally got the chance to sort of connect our 2 different oxidation reaction things together.
Uh-huh.
And I loved learning about how the catalytic converter worked. I feel like it was just a really good episode.
Yeah, agreed. Very interesting.
So is there anything else good that you want to report in your life, Jim, besides this really cool topic, this really good chemistry lesson you just had?
Yes, I'm reporting live. This just in. Actually, I think the only thing I can really think of that I sort of told you I was going to mention this, but just the cool thing that happened this week is that my wife and I got to hang out with Melissa and Mason.
Oh my gosh, that was so fun.
Easily the highlight of our last week. And we just had not gotten a chance to hang out in quite a while. They've been busy. We've been busy. All kinds of stuff. You get it. You know what life is like.
Yeah.
So it was just great. We got to eat dinner. Melissa and Mason cooked. So
yes, we cooked because I don't know if you know that Jam has a baby.
Right.
Which those are supposed to be a lot of work.
Yeah, and they don't do much cooking at all.
No, they do not pull their own weight.
Nope, not at all.
They just sit around and look cute and cry.
Yes, and some babies don't even have the nerve to do that. So, just kidding.
So we usually do like a meal train where everybody comes and brings meals for new parents. So we wanted to do that. So we brought over food. And then we barged our way in and stayed.
Yeah, they also brought over themselves, and we all hung out and caught up, and also watched the first episode of The Rings of Power.
Oh, it was so good. We stayed up so late. Yeah. I was a little zombie in the car on the way home.
And it was really good. We're all 4 of us Lord of the Rings fans in varying degrees. Mm-hmm. And, there's lots of people talking about the show out there or whatever, but we have... most of us not tried to look up anything about it.
Yes, I've seen whispers on TikTok, and that's it. And I tried to kind of stay out of the loop.
Yep, same deal. I don't like spoilers or anything like that. And so watching it with very clear, blank slates, basically, was really fun. And we just watched only one episode, and then we are going to wait till we can hang out again to watch more. So that'll be hard.
It was really hard. But I will say, then the next day... and not to be slighted, we also went and hung out with some of my other friends, old roommates.
Right.
One reviewer of the podcast.
Yes.
And we watched the first episode of season 2 of Ted Lasso. And that was really good too. So, they have seen it. So I was allowed to keep watching that. So that's how Mason and I are filling our hearts up in the middle.
Yeah.
So at least we have that to salve on the open wound.
Yeah, that's very true. Yeah. But it's just enough to be like a sort of an intro and teaser, and then we were like, well, we already stayed up so late. We can't watch another episode.
So tired. Well, and also Jam is really nerdy. I don't know if you guys know. That's probably why he's on this podcast. And he knew so much about the Lord of the Rings universe. We asked a question, and Jam had like 5 minutes of backstory. And you're like, how? And then the next one, same thing. And I thought I knew a lot, but man, he knew more. So that was very, very impressive.
Yeah, it's not come in handy very often, so it was nice, It's like the shoe got to be on the other foot. It's like, I'm the expert here, and Melissa has an interest.
Yeah.
But I'm not really an expert, and actually I know so many people who know way more about Lord of the Rings.
Oh, there are people who speak Elvish.
Yeah.
Which means that he must have made Elvish.
Yeah.
Which means he made a whole language.
Yep.
It's wild.
I know. It's crazy. So I'm really not anywhere close to knowing as much as a lot of people do, but at least relative to Mason, it seemed impressive, which I'll take. I'll take it.
It was really fun. Highly recommend if you haven't seen it. Also, highly recommend just getting time with friends. Emily and I used to very regularly go out to the gas station for a little soda run, and we got to do that on Friday. And it's been a long time. And back before children, we did it all the time.
Yeah, and eating a meal in the home together is so fun.
Yeah.
Very underrated, I would say.
Yeah, I've been eating out lately and consistently disappointed.
Yeah.
I don't know why, although I did have McDonald's the other day and it hit the spot. But Other places have been, I don't know. I just think, oh, if I just made it at home, it'd be harder, but it would taste better.
Yeah.
So get together with your friends, make your meal in their kitchen so that it feels like a party the whole time. That's what we did. And then just eat good food and watch good shows.
Yeah.
And have good conversations.
Yep.
It was the best.
Yeah.
Well, that was fun. We just got to do one happy thing together.
Yeah, I like it.
What if that wasn't my fun thing? What if I was like, oh, yeah, that was all right, but...
I think you would have just felt bad, you know? I think I wouldn't have had to say much. You would have been like, ooh.
Ooh, awkward. Yeah. Well, that was really fun. So thanks for having us over in your house and for letting us hold your babies.
Anytime, and thanks for cooking.
Of course. My pleasure. I'll trade you dinner for hanging out with a kid anytime.
Deal. We'll probably take you up on that multiple times.
And thanks for coming and learning about catalytic converters. I was so excited about this pairing of episodes because there was so much organic chemistry in it. And it's rooted in a lot of other things that we've talked about before, but then it also is a new application. So it's fun to get to see stuff like that crop up. And it's also fun when it's scary and I'd been putting it off for a while and then I was able to learn it.
Nice.
So there's so many fun things about this little 2-part series. So thanks for learning about it. And thanks to our listeners for learning as well. We could not do this if there weren't people out there who cared to learn. I guess we could, but it would just be going out into the universe to no one.
Yes, exactly.
And we would not have gotten this great episode idea without y'all. So thank you so much for giving us all those, all the feedback and questions and listening and being excited about chemistry with us.
And thanks for teaching us all the cool stuff and being willing to do that. The hard part. All of us who are curious to learn, but wouldn't be able to teach ourselves. So thanks for doing that. If you have an idea or a question of something you think is chemistry that you've wondered about in your everyday life, please reach out to us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, FOR, Your Life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/Chem for Your Life or tap the link in our show notes to donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode can be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to A. Molina and S. Navarro, who reviewed this episode.